Our next speaker of our conference is Argo Saakyan. Argo, are you here?
Yeah. Yes, I'm here.
Yeah, welcome to our conference. And Argo is ML and CV researcher at dscamp. Am I right?
Yeah, sure.
And Argo would be talking about Cascade models in computer vision. Argo, go ahead.
Yeah, thanks. Hello everyone. My name is Argo, and I'm going to talk about a cool little technique in computer vision, and we will discuss different real cases where you can use this technique. But let's start with basics. Computer vision is, generally speaking, it is when we use an algorithm to analyze an image. That's pretty obvious. And in our case, we're going to talk about deep learning and neural networks for image processing. And the simplest task is a classification problem. It's where we use a neural network to classify if there is a dog or a cat on the image. So classification is the most basic task. It's not that useful just by itself, but it's a base for other tasks. So in real world, it is really a really common task is a detection task. In a lot of cases, we need to detect an object or to have segmentation. And in an object detection task, we have just two subtasks. The first one is to localize our object, and the second one is to classify that object. And when we find an object, we localize it with a bounding box. We might call it a B box. So computationally speaking, object detection is a lot pricier than just classification. So we should keep that in mind. Let's get closer to real cases where we can make use of an object detection algorithm for solving real business problems. Imagine that we have a lot of security cameras and we want to make sure that our building is safe. Maybe it is a school or a shopping center or some other place, and we want to detect any situation where someone gets in with a gun. It would be really expensive to have a lot of security guards who were watching every security camera. So it would be nice to have a neural network so it can process video streams from all cameras and send an alert if something suspicious is happening. So that's obviously an object detection task, but because the system will work 24/7, we will get false alarms. It is when the model thinks that, for example, a cell phone is a handgun, and it gives a false alert. So we're going to need an operator to validate alarms. Let's talk about difficulties, because there are some in this exact task and a lot of other tasks which are similar when you're trying to create a system which works 24/7, and especially if you're trying to detect some small objects. So the first problem, our solution needs to be fast. It means that it should be able to process a lot of frames per second. And obviously, more cameras we have, more frames we need to process. We can't use infinite amount of hardware because if our solution is expensive, it doesn't make any sense for business. So faster neural nets we have, more frames per second we can process using one server. Second problem, a lot of false alerts. We need to process video stream 24/7. That's more than 2 million frames per day per one camera. That means that even if we have a really low rate of false positives, we're still going to get a ton of alerts that will because we have just huge amount of frames to process. And of course, we can't afford a lot of operators to check if every alert is real. So our solution is going to be expensive again. And the third problem, that's that first two problems don't play well with each other, as it always a trade-off between accuracy and speed. Faster neural nets we have, less accuracy we get, and more false alerts we create. Usually, if we want more accurate models, we need more hardware for running bigger models at needed speeds. But is there anything that can help a little bit with this trade-off? Fortunately, yes, there are several techniques, and I'm going to talk about one of them, which has shown its efficacy in different cases for me. So let's see an example. How can we increase our accuracy without losing processing speed and using the same amount of hardware? We can get pretty close to that with this technique. And the idea is to use two neural networks in a cascade, so one after another. But both nets are tuned in a specific way to complement each other. The first neural net is a fast detector. It runs on the whole frame, but it is downscaled to something like 640 by 640. So it runs on the image and localizes interested object and classifies it. This model should be tuned to have higher recall, sacrificing precision, which means that model will try to always detect a gun, but unfortunately, it will often give a false positive on a cell phone or something like that, something which is visually similar to our interested object, in our case, a gun. And detector should be trained on the relevant to inference images with guns. So we have just one class, and it is a gun, our interested object. The second neural net is a classifier. It runs on the crop made by a detector. So this is important. It runs only if detector finds anything. Specifically saying, we are taking our coordinates from the crop, from the detector, and then crop the original image so we can use higher resolution image for our classifier. In that case, we don't really lose accuracy if, let's say, we have high resolution cameras, maybe something like 2K or 4K. But we want our detector to still work at 640 by 640. So we resize our image a lot and we lose resolution, but we are detecting fast. And in this case, in this exact case, classifier is really good because it just takes original size, takes the crop, and works on that. So the task of classifier is to validate if chosen by detector object is a gun or not. Classifier should be trained on the crops from the detector, but it should have several classes. So not only a gun, but some other objects which are often detected as a gun by our first model. For example, it can be a cell phone, umbrella, bag, or some other things. So one more time, the goal of the detector is to detect an object which might be a gun, and classifier should be able to correctly validate that object. So training both nets is done based on that. And I should also mention that classifier is going to be easier to retrain based on real cases after the deployment. So that's a great thing too. So why does this technique work? Let's first discuss why it is fast. there are two main points. And the first one is that basically the speed of our whole solution is tied to the speed of the first neural network, the detector. It is because our second net runs just in cases where first net finds anything. So 99% of the time, our second net is idle. When we need to run second net, we can do that as a separate process, so our detector doesn't lose any FPS, so it continues working. And as classifiers are generally fast, and ours work on pretty small image, because it's a crop, that's really pretty good. I mean, there is not much computational power needed in this task. And the second thing is that because we have our classifier, we can choose just a fast detector. So we don't need our detector to be big and like really accurate. We just need it to be fast and to find a lot of cases where there might be a gun. So now let's discuss why we gain accuracy. The first thing is that we use an ensemble of models, and that's always good for the accuracy. The second thing is that our classifier, the second model, gets full resolution part of the image. Next, we use different data sets for our models, and our classifier is tuned to distinguish guns and other similar objects. I think this is the most important part, that we not just use different models. We have different data sets and we have different classes. That's important. Next, from detector, we need good detection, and from classifier, good classification, which is pretty obvious. So we can choose models based on that. I mean, model architectures. We don't need to sacrifice classification power of the detector just because it is fast. So in this case, we will end up with the best fit on the detection side and on the classification side. And the last point is that we can easily retrain classifier after deployment, as I've said, and new objects, which are often detected as a gun. We can use that to retrain our classifier, and that should not affect detection scores. I mean, of course, you can retrain detector too. You just need to do more work. That's about labeling. And with classifier, it's a lot easier to implement. Yeah, here are some metrics. As you can see on the right side, we have slightly decreased recall, but noticeably increased precision. What does it mean? It means that we can't really detect every situation, but we noticeably decreased false positives. And that is important for our task, because remember, we don't want to spam two operators, because if we do that, our system doesn't make any sense. No one would want to work with it. A couple of words about the dataset. There are general rules that you should know about. Of course, you should remember to collect balanced dataset, diverse, representative, have a good and consistent labeling, and so on. But I want to mention a couple of specific things. For the detector, you need to collect data as close to inference as possible. If your inference is going to be on security cameras, you would want to collect your dataset on cameras close to that ones. For sure, you need to place it correctly, to have correct angles, just how inference cameras are going to have. Your objects in the frame should be close to inference too. So in an example with a gun, you don't need to bring a gun to 10 centimeters in front of the camera, because it is not realistic. And for sure, the first image is not realistic. It just doesn't make any sense to use anything like this in the dataset. But the second image is a good one because it is actually taken with a security camera. So it is close to real case, to real scenario. And for the classifier, you would want to create a lot of crops from your detector. It's a good idea to run a detector with lower threshold to get a lot of false positives. So you want your model, your detector, to give a prediction on something like a cell phone. You want to collect that images to use it later. And how should you use it? You should analyze images and select groups like cell phone, as I've said, if it shows up often. If you can create a separate class with it, you should do that. So, for example, we have collected 5,000 images of guns, and we have around 3,000 false alerts on phones because we have a low threshold. That means that we should take a cell phone and create it as a separate class for our classifier. Then we should do that to all classes that we can. And of course, we're going to have some things which are rare in our false alerts. And we should use it for our last class, which is called like other. There is everything which we cannot use in a separate class. So with all of that, you should have an OK dataset for your task. And when I'm talking about dataset, because it is like really important, it's probably more important than models. So you should really work hard on the dataset. I'm also mentioning deployment slightly. Remember that I said that our solution needs to be fast. That's really a problem in real case tasks. So deployment is critical. We obviously cannot just train a model on PyTorch or TensorFlow and call it a day. I highly recommend converting your model to TensorRT. TensorRT is basically an optimization for NVIDIA GPUs. And that will help you to make your model like 5 times faster. I'm saying that based on real case, so not just metrics from NVIDIA, like on this photo. I'm talking about real projects. And also, which is good, you will need less VRAM on your inference. What's next, by the way, what's next with PyTorch, you can also have a look to Torch script instead of TensorRT, but TensorRT is probably better. The second thing about deployment is that you should have a serving software such as Triton Server from NVIDIA, or TorchServe or TensorFlow Serve. And it's like a backend where you store your model and then send requests with images for models to process. That will help you with scaling your model, and that's pretty important. And finally, let's see some examples, so you know where you can start if you will have some similar task. So these are just examples of the models that are great to use. It might be your baseline, for example. As a first neural network detector, I often use Yellow V5. There are several models from nano version to extra large, so you can choose. The smallest ones are faster, but with lower accuracy, obviously, and the bigger one are slower, but more accurate. Yellow V5 is good because it is state of the art for speed and accuracy. and it converts to TensorRT really easily. So really keep an eye on that. And by the way, just a couple of days ago, we got YOLO version 8. There are like 6th version and 7th version. I tried them, but I didn't really find them better than YOLO v5 based on speed and accuracy. But if we would look to the metrics from YOLO v8, it's pretty impressive. So you should definitely try it out. As our second model classifier, I often use EfficientNet from Google. It has also different sizes, around 8 sizes. So again, you can choose. By the way, I had some issues with TensorFlow's version of EfficientNet while converting it to TensorRT, but you could try PyTorch. It should work better, I guess. All right, and let's sum up. When you need to deploy an object detection solution, which is going to be 24/7 system, and you need to increase precision without sacrificing speed, try using a classifier as your second model, which runs on the crop of the detector when it finds something. That should be a good solution. So at least you can try and see how it will work on your case. And that's it. Thank you very much.
Okay,
I'm ready to answer any questions.
Yes, there's a question from Yulia.
Yeah, give me a sec. So are there any problems with the dataset? How do you deal with them? If yes, do you mean are there problems like in real cases, or in which data sets? I will just answer for now the second question. Yeah, collecting data. Yes, the data is the hardest part, I guess. You should collect your own data, and it is always really important to create a pipeline for a group of people who are going to collect that. They are going to have a lot of mistakes, so it is pretty big work for collecting a good data set. And if you have more than one person who is labeling the data, you should first talk to each other and understand how are you going to label some cases, like corner cases, when it's not really obvious how you should label that case. If one person labels in one way and second one in another way, it is going to be bad. If you label it the same way, that is going to be better, like a lot better. The second question, how do you usually collect the video data from cameras? There are a couple of ways, and I prefer getting a baseline model, then collecting a video stream from a camera, then using a custom script just to create like a lot of frames from that video. We don't want to take every frame. We can take like 1 frame per second, for example, and then we run our baseline model on created frames. And then we give the data to labeling team. They will label cases where our model cannot find the object, or it does it poorly, or with low confidence level. So it is a way to fastly grow your dataset and collect valuable data. How to implement those 2 CNN models, training in raw using Python. With the output of the first CNN for detection problem and an input for the second one, for the classification problem. Can you share a repo? If we're talking about how first model works with the second, you are not going to give output of the first model to the second one. What you want to do is to get the prediction like a B-box coordinates. Then you go to your original image and then use that coordinates to get that crop, that object from the original image. And then you get you give that crop to a classifier that helps with if you would just give output of the first model, it would be low resolution. That you don't want to do that. So you take coordinates and crop it from the original image. How to implement those two CNN models training in a row using Python? So you are going to train them separately. Detector is going to be first. You are going to train it, get a baseline, then run it on a lot of like all your data. It will create your crops, and then you will create from that crops your data set for your second model, for your classifier, and then you will train your classifier. So training is not going to be in a row, one after another. And speaking about GitHub repo, if you want if you want to know how to train them, it is just usual training. Like if we're talking about Yellow V5, you just use their documentation to train Yellow model, and your CNN model, you train like the usual CNN model. But if you are talking about deployment, so how to inference and run your models one after another, yes, I can share a GitHub repo. I will do that in a chat just in a couple of minutes. Thank you.